Okay, so last we were meeting up, we had talked about the difference between physical and chemical reactions. And we did a couple of balancing chemical equations. So what I'm going to do is we're actually going to pick up there. And so I'm going to put a couple of equations on the board. And then I want us to sit there and go through the process of balancing them. I'll show you guys, and then I want you guys to kind of help me walk me through it. So that means you guys are going to have to interact with me a little bit. Let's see. Okay, so let's say we'll start with something simple like, okay, so first off, we're going to talk a little bit about the law of conservation. So that kind of helps us understand things. So the law of conservation of matter says that um, nothing can be either created or destroyed. It can only be changed. Okay. Another way of saying that or thinking about it is what you put in, you have to get out. It doesn't have to be the same form, but it has to add up on both sides. Okay. So when we balance chemical equations, it's the law of conservation. When we balance chemical equations, we want to make sure that what we're putting in, we're recovering, right? And so they may be in a different form, but we're recovering. And that's one of the difference between a chemical reaction and a physical reaction. Because if it's a physical reaction, the identity isn't going to change. So in a chemical reaction, the identity changes. So for here, for example, we have hydrogen gas, and you guys are able to see the equation on the screen. A thumbs up, acknowledgement, something to let me know that you're there.
Yes.
Okay, good. Okay, so we have hydrogen gas. Now this plus is going to mean and. It's like hydrogen gas and oxygen gas. This here is called the yield sign. And the yield signs, we kind of use it as to make, right? So it's going to make water. Now, the little g here represents, so little g is going to represent gas. L is going to represent liquid. S is going to represent solid. And AQ is going to represent aqueous. Now, the term aqueous means dissolved in water. Okay. Okay. So are you guys all able to hear me? Were you guys not able to hear me earlier?
I do.
I can hear you now.
You can hear me now?
I can hear you.
Okay, good. Okay. So this, we'll draw it in a different color. So this number here is called a subscript. Now the subscripts tells us when it's right next to that element, it tells us how many of that element we have. Thank you. Okay. Okay, so in this case, hydrogen has two. We have two hydrogens. In the case of the oxygen, how many oxygens do we have? Or oxygen elements or atoms we have? Right here, two. Okay. And then if we go over here to water, now water is going to be a compound. Okay. Now we call it a compound because it's composed of two or more different atoms. We can also call it a molecule. Definition of a molecule Let's see. Okay. And a molecule is going to be two or more atoms. Okay. So water is a compound. Oxygen gas is a molecule because it's composed of two or more, right? Water is composed of two or more different because it has hydrogen and it has oxygen. And then oxygen gas only has oxygen, but there's two of them. So this would be a molecule. And then this would be a compound. Okay. Are you guys kind of clear on that? Okay. So when we're doing balancing chemical equations, it's like keeping tally. And we're going to try to keep tally and balance them by using what we call coefficients. Coefficients are the numbers that are going to be in front of our, in this case, our molecules to let us know how many of those molecules that we need to make our product. So the way you always start off is you want to start off by writing down the elements that we're looking at. And so what I always do, I put them like in the center here, right below the arrow. So I have hydrogen and I have an oxygen because water is composed of hydrogen and oxygen. So this side is called the reactant side. And I know I'm repeating myself, but it's okay. This side is called the product side. Okay, so on my reactant side, how many hydrogens do I have?
Two.
How many oxygens do I have?
Two.
Okay, so we have two hydrogens and two oxygens. Again, that's told to us by the subscripts. Now, if we go on our product side, how many hydrogens do I have?
Two.
And then how many oxygens do I have?
One.
One. Okay. So one important factor is that when there's no number there, it's always understood to be one. Okay. So now I'm going to ask you a really hard question. And more than Jocelyn can join in. Feel free to join in. So is this balanced? Meaning that are the numbers on both sides, the reactant side and the product side, equal to each other? No, that's right. Okay. So the way that we're going to get them to be equal to each other is by introducing the coefficient. Okay. So on our product side, we know we have, on our reactant side, we had two hydrogens. On our product side, we had two hydrogens. On our reactant side, we had two oxygens. On our product side, we had one oxygen. So what do I need to multiply my product side so that I would end up with two oxygens? So one times what equals two?
Two.
Two. Okay, so we're going to go ahead and put a two in front of the water molecule. Now, when we do this, that means that this 2 is going to be multiplied by our subscripts, and that'll tell us how many we have. So in this case, 2 times 2 is going to be
4.
4. And then 2 times 1,
2.
okay? Okay, so then our oxygens are good. So now on our reactant side, we have to get that balance with the product side because we have 4 over here. So what can I multiply my hydrogen gas by so that I would end up with 4?
2.
2. Okay, so you just confirm we have 4 here, we have 4 here, so that's balanced. We have 2 here, we have 2 here, so that's balanced. So now we have a balanced chemical equation. So are you guys good?
Yeah.
Okay. Okay, so we're going to make it a little bit harder. So let's assume that we have okay. So in this equation we have this is called sodium sulfate is going to be reacting with Gol3 chloride. And then we're going to be producing Gol3 sulfate and sodium chloride. Okay, now under these circumstances, we are introducing a new symbol. We're putting in the parentheses. Now, what the parentheses mean so what the parentheses mean, that basically means that the number on the outside is being multiplied by what's on the inside. So in this case, it's going to be multiplied by both the sulfur, which is the S, and the oxygen, which is the O. Okay. So in this case, we're going to go ahead and put the numbers down. I mean the elements. So Na is sodium. And do you guys have your periodic table available? For those who don't know, who may not know, you guys that are in Kalinga, Lemoore, or in Fireball, I have packets that have the periodic table on them available at the Mesa Centers in Kalinga, Fireball. And then Harnell, you guys were handed out those during lab. And so you want to pull those out so it'll help you with your elements. So we have sodium, we have sulfur, we have oxygen, we have gold, which is AU, and we have chloride. Okay, so on our reactant side, how many sodiums do we have? On our reactant side, over here. So how many NAs do we have? We have 2. So Na is sodium. How many sulfur? S is sulfur. How many sulfurs do we have?
1.
Okay. How many oxygens do we have?
4.
How many gold?
1.
And how many chlorine?
3.
Okay, so on our product side, how many sodiums?
1.
How many sulfurs?
12.
Not 12
Or
because
sorry, 3.
that's right. We have 3. So there's nothing next to that S, but on the outside we have a 3. So 3 times 1, that's going to give us our 3. So we're going to do it like this. And then how many oxygens?
12.
How many gold?
2.
And how many chlorine?
1.
Okay. So I'm going to ask you a hard question. Is it balanced?
No.
No. Okay, so we know that it's not balanced. So now we need to go through the process of balancing it. So there's a couple of ways that we can go through that process. The easiest way is to find the one that looks like it's the easier to work with, right? So like, for instance, if we look at our goal, on one side we have 2 goal, on the other side we have 1 goal, right? So what can we put in front of there so that it would end up being 2 on both sides? So on our reactant side, what do I need to put in front of that? My goal.
2.
2. So then that would give me 2 gold. And then how many chlorines would I have? How many CLs? So now I have this number in front. Now this number in front is called the coefficient. Again, type that out. That's what this is. So again, this is going to be distributive. So then how many chlorines do I have?
6.
I have a total of 6. So distributive basically means I just multiply it by both elements that are there. So anytime you have a coefficient, it's going to be multiplied by the elements that are in that compound. Okay. So then if I go to my reactant, my product side, what do I need to put in front of my sodium chloride, my NaCl? So I have how many chlorines on my reactant side? How many do I need to, what do I need to multiply 1 by so that it would be the same?
6.
6. So I'm going to put a 6 in front of as my coefficient for my sodium chloride. So that means that now I have a total of how many sodiums?
6.
That's right, 6. And then how many chlorines?
6.
6. Okay, so that's looking good. My goal is looking good. So now I can go up to my sodiums. So I have 6 on one side and 2 on the other side. What do I need to multiply it by so that I would end up with 6 on my reactant side for my sodiums?
3.
3. So I'm going to put a coefficient of 3. So 3 times 6, 3 times 2 is 6. And then how many sulfurs do I have on my reactant side now?
3.
Okay. 3 times 1 is 3. And then how many oxygens do I have?
12.
Okay, so let's check it out. So I have 6 sodiums on my reactant sides, 6 sodium on my product side, 3 sulfur on my reactant side, 3 sulfur on my product side, 12 oxygen on my reactant side, 12 oxygen on my product side, 2 gold on my reactant side, and 2 gold on my product side, and 6 chlorine on my reactant side, and 6 on my product side. Okay, not too bad. How you feeling?
So far, pretty good.
So far, pretty good. So shall we try another question?
Yes.
Okay, so just for the record, this reaction is called a double displacement reaction. In other words, you're changing partners. The sodium is going to be connecting with the chlorine, and the gold is going to be connecting with the sulfate. This guy is called sulfate. And so that's why it's called a double displacement reaction. And you'll learn more about that later on. Okay, so let's try another one. And then this time, I'm not going to say anything. I'm going to let you guys work it out. And then you guys are going to tell me what I need to write on the board. Is that cool? And you guys can talk with each other, help each other through the process. Oops, let's see. So this reaction is called a combustion reaction or an oxidation reaction. So we have, this is called ethane. It's going to be reacting with oxygen gas, which is going to be reacting with carbon dioxide, which is going to be reacting with water. So just for my benefit, I want you guys to do something for me and respond to me right now, and then I'll let you guys work on this. So is this a molecule or a compound or both? Based upon our definition of molecules and compounds.
Both.
It's both. That's right. Because the definition of a compound is 2 or more different atoms. Okay. What about the oxygen gas? Is that a molecule or a compound?
Molecule.
It's a molecule. Okay. What about carbon dioxide, CO2?
Compound.
It's a compound. Is it a molecule?
No.
It is, because the definition of a molecule is 2 or more atoms. How many total atoms do we have here? We have carbon and we have oxygen, 2 oxygens, right? So that'll be a total of 3 atoms. So that's 2 or more. Okay, what about water?
Compound.
That's right. It's a compound and
Molecule.
a molecule. Okay. Okay. So I'm going to let you guys talk with each other and work it out. I'm just going to sit here and eavesdrop a little bit. Okay. Well, I take no answer as a yes. Okay. So what is the first step that we're going to do?
We list the individual elements.
Okay. So I have a C, I have a H, and I have a O. So I have carbon, hydrogen, and oxygen. Okay. So what's next?
We check the number of carbons on the reactive side.
Okay. So how many carbons do we have?
2.
How many hydrogens?
6.
Okay. And how many oxygens?
2.
Okay. Good job, guys. On the, what's next? Sorry, I get excited. I want to tell you everything.
So on the product, carbon has 1. And hydrogen has 2. Oxygen has 3.
That's correct. Because we have 2 here and we have to add that 1 that's on the water as well. Okay. So is it balanced?
No.
That's right. It's not balanced. Okay. So what are we going to do next?
I tried balancing the carbon. So
Okay.
I placed 2 in front of the carbon at the product side.
Okay. So then that means that we did it with 2 carbon. How many oxygens? Now, let's see. Okay, so we got 4 here, and then we have an additional 1 on the water. So we have a total of 5. So 4 from the carbon dioxide. So that's 2 times 2 plus the 1 that we'd have over here. Okay. So is that balanced? No. Okay, so what do we need to do next? So we have our carbon. They look like they're balanced right now. What about our hydrogens? How are we going to get those to balance? What should we put in front of the water to get us started?
3.
A 3. Okay. So then we have a 3. So 3 times 2 is 6. 6 hydrogens. And then we have 4 plus 3 oxygens. So 4 plus 3 is 7, if I remember correctly. Okay. Are you guys still there or did I lose you? Can you guys hear me?
Can we take the oxygen side again?
Oh, how many oxygens do we have? So we have a total of 7. So we have 3. We have 2 times 2, which is 4. And then we have 3 times 1, which is 3. And then that's going to add up to 7. Okay. So now we're going to have to go to the product side, right? Okay. So what times 2 is going to be equal to 7? What times 2 is going to be equal to 7?
3.5.
Okay, 3.5, or what we often will do is put 7/2 because we like those whole numbers, and I'm going to show you how to get to those whole numbers. So 7/2 times 2, which is 3.5 times 2, that's going to be 7. So then that would give us our 7. Now I'm going to ask you a question. So if I took Jinxie and I cut Jinxie in half, would Jinxie be okay? Anybody can answer this. We'll say split him right down the middle.
No.
No, he wouldn't be okay. Okay, now that's going to be the same thing if we're talking about a single molecule. If we split it in half, it's not going to be okay. Okay, so we don't want to leave it as a half or a 0.5. So what can I multiply the whole equation by so that I can get rid of that half? So what times 1/2 is going to give me a whole number? So let me write that down. So 1/2 times what? Question mark. Is going to give me 1. So what do I need to multiply 1/2 by so that it will equal 1?
2.
2. Okay, so what we're going to do is we're going to multiply this whole equation by 2. Okay, so let me write down the chemical equation down here. Okay. Okay, so 2 times the coefficient here. So since there's nothing in front of it, it's assumed to be what number?
1.
1.
That's right. It's assumed to be 1. So 2 times 1 is 2, right? And 2 times 7/2 So that's the 2's are going to cancel out. So we're going to be left with 7. And then 2 times 2.
Four.
And 2 times 3.
6.
Okay. Okay, so this would be our chemical equation. I'm going to go ahead. You guys mind if I erase this to give us a little more room to work? And then I'm going to pull this up. So now we want to confirm to make sure that we're right, because you don't want to do all that hard work and then be wrong in the end, right? Okay, so let's go ahead and write down our elements. So we have C, O, I'm sorry, be consistent. C, H, and O. Okay, so on our reactant side, how many carbons do we have?
Yeah.
We have, remember the coefficient in front.
Oh,
So we're looking down here at the bottom. So 2 times 2,
4.
4. Okay, and then our hydrogens, we have 2 times 6.
12.
And then our oxygens, we have 7 times 2.
14.
And then on our product side, we have 4 times 1.
4.
Our oxygens, we have 4 times 2
Is 8.
6.
plus
6.
6. Okay, so that's 14. And then for our hydrogens, we have 6 times 2.
12.
Okay, so what we put in, we have to get out. So it's balanced, right? So we call this in chemistry balancing chemical equations. Okay, how are you guys feeling on it? You have about 10 of them on your homework assignment. So it'll give you more practice, and we'll probably do each week, every week, we'll probably end up doing a couple of more because that's just part of the nature of the beast. Okay. So, and this one is a little bit harder because of the 7 halves. So anytime that you have an even number and an odd number on the other side, then that typically means that either we have to find a creative way of making it work, or you're going to end up using a half number when it comes from a single source. Okay.
How did we get the 14 for oxygen on the product side?
So we have 4. Let me see. I'll draw it out here. We'll use the green. So we have our 4 times our 2, which is 8. And then we have 6 times 1. So 8 plus 6. And that's going to equal 14.
Okay.
Okay. Okay. So I have a question. So what does the plus mean? This plus here. Okay, so we got to establish some rules. So one of the rules is we're not going to be worried about being wrong. It's okay that we're wrong. It's better for us to be wrong in lecture than on the exam, or to be wrong in lecture than you know, dealing meds to a patient or anything like that. So it's okay to be wrong because that's how we learn. Okay. So what do you guys remember? Do you guys remember what I said the plus means? What does this symbol mean? If I draw that, what would that mean to you? If I said Mary here, and I put that symbol, and so what does that mean? This symbol here.
Like they are together.
Or we would say that Mary and John, right? And, right? So you're saying this and this is going to make this and that. Okay. So that plus is kind of like saying and, you know, and so the reason I'm stressing that is because a lot of times, particularly students that are just beginning out, they'll often think of it as, when we put the coefficient, they'll try to put the coefficient for everything. The coefficients are only going to pertain to the one that it's in front of, the molecule that it's in front of. So you have two molecules that we're looking at. Okay, so this is not just one compound. Does that make sense?
Yes.
Okay, good. Okay, so let's see. Let's go back to the lecture. Okay, so we've talked about balancing chemical equations. We've talked about compounds. Um, we've talked about compounds and we talked about molecules. Uh, we also have ways of defining matter, right? So when we make reference to something being pure, a pure substance. Now, a pure substance doesn't mean that it's only a single element, right? It means that it could be a compound that is pure, like pure cane sugar. It's all sugar, right? Um, it's just one kind of matter. So it's just one type of thing. So if I have pure salt, so that I have pure NaCl, that means there's nothing else in it except NaCl. And so we refer to that as a pure substance. A mixture is going to be two or more pure substances mixed together. Okay. So how many of you guys have ever made Kool-Aid? Wow, total different generation. Usually I say that and there'll be tons of people, oh yeah, I've made Kool-Aid. Have you heard of Kool-Aid? Wow, this is going to be a rough class. Oh, I have one person that said yes. One person has heard of Kool-Aid. Well, that's good. Okay, so let's talk about Kool-Aid. Kool-Aid is a packet of flavor, and then you add the sugar yourself and you add water. Okay. Now we put these all together. Is that a pure substance?
It's a
No.
mixture.
It's a mixture. That's right. Okay. Because it's three independent pure substances that are added together. Actually, it's more than that because that Kool-Aid packet has about 5 different things that are in there. So often we're going to be working with mixtures and we use mixtures all the time. Like we do it for Kool-Aid. How many of you guys have cocktails? Anybody old enough to drink? Okay. Well, that's also good to know. So most of you guys are not old enough to drink. Is that what you're telling me? So you've never had cocktails. Have you had the Slurpee? Anybody have Slurpees before? Yes. Okay. So now when we talk about the Slurpee, now do you guys go there and you mix them? You know, you have the blue one and do the red one and do a white one. So it's like the American flag, red, white, and blue. Anybody ever do that? Coke, yeah. The red and the cherry and the Coke. I do that quite a bit, right? Okay. So in that case, right? So that would be an example of a mixture, right? And that's how we recognize it. And so we use mixtures all the time. And often we'll use it to our benefit. How many of you guys cook? Nobody? Has anybody ever made pasta or ramen noodles? Okay, good. Okay, so now do you guys add salt to your water if you're making pasta, like you're making spaghetti? Yeah. Why do you add salt to your water? Anybody? Boy, this is a rough crowd. Do you guys add it for the flavor? Yeah, I like it. For the flavor. Most people add it for, don't get me wrong, I love salt. That's one of my problems, right? It's probably why my blood pressure's up because I like salt. So often we do add it for the flavor, but that's not the real reason. You know, we think that, but the real reason that we added salt to our boiling water for making pasta is so that the water gets hotter and it cooks the pasta faster. So you don't end up with soggy noodles. Anybody like soggy noodles?
No.
This is an example. So water boils at 100 degrees Celsius. We talked about that last week. And if we add salt to it, it actually causes the water to boil at a much greater. The more salt that we add, you know, then the longer or the hotter it'll get. Okay. And so if we add salt, in this case, we're adding salt to our water. So we call, when we have a mixture of things together, we'll call it a solution. So our salt water solution will actually boil at a higher temperature. And you can see here where water will level off. That salt solution will kind of continues to shoot up. So it'll continue getting hotter and hotter and hotter. It'll start boiling eventually, but it will get hotter and hotter and hotter depending on the amount of salt that you have. Okay. So we're actually changing what we call the boiling point. So often by adding something to a mixture, you're going to change your boiling point. In most cases, you cause it to be higher than what it normally would be. So it takes more energy to cause it to boil. And so then in that case, your water's a lot hotter. You throw your noodles in there, and then they cook faster, and they're not going to be soggy. Okay. And so that's one of the benefits of using, you know, a mixture. Not only that, this also lets us know that that is going to change the physical properties of water. Boiling point is one of the physical properties of water. By us adding salt, it changes those properties, those physical properties. Okay. So often we'll be mixing things together. And so we have to think about it, whether it's going to be a pure substance or whether it's going to be a mixture. So if we take a look here, so this here represents bromine. Okay. Bromine is Br, that's a symbol. It's also a diatomic element. I'm going to type that out. And then I'm going to tell you a little bit more about diatomic elements. I might type that out. Okay. Diatomic means two atoms. That's what it means. Di means two, and then atomic means atoms. So bromine is one of the 7 diatomic elements. And there are 7 of them. Bromine is one of them. Now, that basically means that when we write bromine, it's always going to be written as Br2 when we're talking about bromine by itself. When it's in a compound, it's different. But when we're talking about just pure bromine, it's always Br2. So in this case, we have pure bromine, we have pure water. Okay. Now, bromine is all bromine. It's pure. Nothing else is there except the bromine. And over here, the only thing that's there is water. And these are representing they're models for the water, the bromine and the water. Now, this here is going to be we're adding bromine and water together. So is that going to be a mixture or is it going to be a pure substance? If we have a small amount of bromine and a whole bunch of water. Now it's written on the screen. You guys should be able to tell me this one, right? So we know that this is going to be a mixture. In both cases, they're going to be mixtures. Whether you have a small amount or you have a large amount, they both will be mixtures because it's no longer pure. Okay. So when I was a kid in growing up, my family, when we went out to eat, it would always be something big. You know, we'd have to do some type of big event, something big had to happen. Like somebody got a new job or something like that. Otherwise, we would never go out to eat. But one of the places my dad likes to go is Denny's. And so like he got this new job. He was working 2 jobs and he got a new job. And so he took us out to eat to Denny's. And so we would sit at the little booth, and I'm kind of dating myself right now, but they used to have the jars with sugar, and then you'd have your salt and pepper shakers, right? And so what I used to do is I would actually go and I would dump the salt in the sugar, and then I switch it over with another table, and then I'd watch to see what they do when they added the sugar to their coffee. And so if you guys think about it, salt and sugar, what are the physical characteristics of it? What does it look like? What color is it? White. Okay. That's right. It's white. And so they look alike, right? Can you guys tell the difference between salt and sugar other than tasting it? No, you really can't. And because of that, yeah, and because of that, yeah, it's the only way that I can take, only way I can tell is by tasting it. And so because of that, when we put them together, is that going to be a mixture or is that going to be pure substance? That's right. It's going to be a mixture. That's right. Okay. Now, when we define mixtures, there's 2 types of mixtures. So let me give you another example. So if I put salt and pepper in the same jar, right? Can I tell the difference between the salt and the pepper? Yeah. Okay. So that is called a heterogeneous mixture, right? Hetero meaning different. Like if you talk about a heterosexual, right? That means that it's different sexes, right? So the same thing that we use for talking about solutions or mixtures. If it's heterogeneous, you can tell the difference between the 2 substances. So like for instance, if I put oil and water together, right? Oil and water together, I can tell them apart, right? If I mix them together, because doesn't oil float up to the top and right? Yes, no, maybe. Okay. So um if it's all the same, all uniform, like for instance, this bromine, if we look at the image here, it's basically showing us that this is all uniform in appearance, the way that we look at it. Since it's all uniform in appearance, we would call that homogeneous. Okay. So heterogeneous, meaning uniform in appearance and properties throughout the whole thing. So if I get a rum and Coke, right? When I mix rum and Coke together, it looks like it's all the same. You can't tell the difference between the two, even though there are 2 different things in there. Or Coke and water. If we mix those together, you can tell the difference between them. But have you guys ever put milk and orange juice together? Anybody ever did that? No. Okay. Well, if you ever try to do that, Like take a little bit of milk, take a little bit of orange juice and put it together and see what happens. And then you guys can tell me whether it's homogeneous or heterogeneous, right? Heterogeneous basically means that it isn't uniform throughout the composition. So you have different phases, so you can see the different phases between the two. So like, I'll give you a hint. When you put milk or orange juice into milk, it looks like it forms a little brain, okay? And so it's going to be easy to tell the difference between your milk and your orange juice. My phone is blowing up. Everybody's remembering it's my birthday at the end of the day. So I apologize. Okay, so oops, let me clear that. We were talking about diatomic elements, and then we'll come back to homogeneous. So, ooh, man, I'm getting carried away. Let me go back. Clear. For some reason. There we go. Okay, so diatomic elements. So I mentioned that there are 7 diatomic elements. Okay, so, and the 7 diatomic elements are, write this out. Okay, so this here is called an anagram. It's just basically help us to remember things. Okay, so have no fear of ice cold beer. Have is going to be for hydrogen. No is for nitrogen. Fear is for fluorine. O is for oxygen. Ice is for, or I is for iodine. C is for chlorine. And B is for bromine, or beer is for bromine. Okay. Now the symbols that we would write them. This would be H2. Nitrogen is going to be N2. Fluorine is going to be F2. Oxygen is going to be O2. And iodine is going to be I2. Chlorine is Cl2. And bromine is Br2. Okay. Okay, so those are your 7 diatomic elements. The reason they're called elements is because they're all the same, right? and they're diatomic because you have two of them that are there. Okay. Any questions on that? Any questions on homogeneous and heterogeneous? Okay. Okay. So this here is just basically showing us again, this here is a pure substance. Now, the misnomer is, even though your book says it, technically a pure substance is not homogeneous. Homogeneous makes reference to it being a mixture and it's looking the same throughout. So if it's written, and I need to make this correction on my slides, we should cross out that is homogeneous, because technically it isn't homogeneous because it's not a mixture, it's a pure substance. And so if we have pure water, it's not homogeneous. If we have pure ethanol, it's not homogeneous, it's a pure substance. If we have a mixture of water and ethanol, you can't really tell it apart, right? But then we know it's a mixture. Now, the beauty of it is, if it's a mixture, there's probably a way that we can just separate those two pure substances from each other. One example is in the case if we have iron and sulfur that are mixed together. Well, we can use a magnet to sit there and separate the iron from the sulfur. And so we can use physical properties to sit there and separate the two. Okay. So some modes of separation of mixtures, one of the major modes is distillation. Distillation is separating mixtures based upon their boiling and condensation. So different compounds boil at different temperatures. And so things will boil off at a lower temperature compared to other temperatures. So for instance, alcohol and water. So alcohol boils at, I believe it's 86.3 degrees Celsius, and water boils at 100 degrees Celsius. So if we have our temperature below 100, but above 83, then the alcohol should boil off. And so we're able to sit there and separate alcohol from water. And then we can use condensation to bring it back down and collect only the alcohol, leaving the water. Now, sometimes, because there are interactions between alcohol and water, sometimes a little bit of water will go to it. So then we'd have to go through that process again to separate it again. Okay. And I'll show you an example of that here in a minute. And so this relies only on the physical characteristics of those two things that are in the mixtures, or the multiple things that are in the mixtures. Now, filtration is the process of passing something through a filter to separate through a filter. How many guys make pots of coffee? Or have seen people make pots of coffee? Most of you guys go to Starbucks now, so. Yeah, no, maybe. Okay. You have? Good. Good. Okay. So, in the old days, we actually had to make our own coffee, people to make it for us. So we would take those grind coffee beans and then we put them in a filter, and then we run water through it. Now, the filter works in a way that it would keep the grinds from being part of the coffee that you're making. And so you would just end up with pure coffee with no grinds if you did it right. Now, if you put too much coffee beans in there, a lot of times it's spilled over, but that's a different story. So in this case, you're separating things based upon size. Those grind coffee beans were bigger than the water that was able to pass through the filter. So here's an example of a distillation column. So here we have our solution that's being distilled. And so we're separating one thing from the other. So we heat it up. And what'll happen is that it'll actually boil. We keep track of the temperature because we want it to only be a certain temperature so that we're favoring one of the mixtures and not both of them. And then what happens, we make the steam goes through this column here, and this is called a condenser. So we run cold water in here and cold water out of here. And then it runs it around the tube so that all of the gas is able to cool down and become liquid. So we're going from the gaseous phase to a liquid phase. And so then we're able to collect the pure liquid on the outside in the beaker. I mean, in the flask here. So this is an example of gravity filtration. So in this case, we have a mixture that's solid and liquid. We pour it through that filter, kind of like the filter paper we talked about with coffee. And then the solid gets stuck up here, and then the liquid, the homogeneous liquid, is able to come out through here. And so this just shows you how to fold the filter paper, fold in half, fold in a quarter, and then you end up with this. And so you guys will probably be doing that here soon if you guys have your kits. For those who are in Kalinga, that are taking the course in Kalinga. Okay, so when we talk about our pure substances, we have elements. And so those are the things that are on our periodic table, or we could have diatomic elements such as oxygen gas or hydrogen gas. And we also have compounds, which you guys already know what compounds are. Okay, so both of those can be pure substances. So when we talk about separation, if we have a mixture which is impure, right, we can separate those by physical means. So you can separate them to your compounds or to your elements or to your molecules. If you have a compound, you can only separate the elements from each other by chemical means. So if you have a pure compound, you can break those down into their elements by a chemical reaction. And so here's some examples of some common elements. So here we have some gold. We have CD is basically silicon. Same thing with our chips here. We have iron. We have lead. We have the carbon in our pencil. And technically copper pennies, although those are alloys now. They're no longer pure. And here's copper wire. And so over here we have various compounds that we see used commonly through our household. So for instance, we have boric acid, we have lye, we have chalk, we have, I guess, an antacid, two forms of antacids, it looks like. And we have baking soda, okay? And then, of course, this is a rock salt, so sodium chloride, okay? So when we talk about the symbol for our elements, they're going to be either one or two letters. And they're going to be used to kind of abbreviate the chemical elements that we're talking about. So H is for hydrogen, He is for helium. Now, we always want to use a capital when we're making reference to that. We don't use a lowercase. Capital lets me know what it is, because if you use a lowercase, you could be talking about something else, particularly when you're putting things together. So let me give you an example. Let's pull up the periodic table. Here, let's see. And I may let you guys go a little bit early, so this lecture might be shorter than all the rest, so that you guys can have a little bit of time to enjoy your Valentine's Day. So. Periodic table. Okay, so this here's our periodic table. And the thing about it is that if you take a look at it, it gives us our symbol. It gives you the full name, it gives you the weight. We call this the atomic mass or the atomic weight. And it gives you up here, this is called our atomic number. So top is atomic number, the symbol, the name, and the atomic mass or the weight. Okay, and so what I was explaining to you is that we want to make sure that we're using capital letters. So for instance, if I wrote two lowercase letters, we'll do come on. So if I wrote HO lowercase, we wouldn't know what that is, right? That could be making reference to holmium. It could be hydrogen and oxygen, right? So we always want to make sure that we're using the appropriate symbol, the way it's written on the periodic table. So if we're talking about holmium, we want to write H lowercase o. Or if we're talking about hydrogen and oxygen, so then we're going to write H O, capital O. Okay, so then this lets me know that I'm talking about hydrogen and oxygen, and this lets me know that I'm talking about holmium. Okay, do you guys understand that? So it's very important that you guys do that, particularly when you're balancing chemical equations and those things. And those are one of the things that I will always deduct on, because you want to make sure that you guys are writing it the correct way. Okay, let's see. Okay. Oops. Okay. Okay, let's see. Okay, so when we talk about chemical formulas, so they're going to be the chemical and then, or the element, and then we're going to also be playing around with the subscripts. So that lets us know. So for instance, this here is sodium, right? So sodium is just Na. This here is hydrogen. So this again is a diatomic element. There are 7 of them, which you guys should know. Now, if I have NaCl, it's no longer just sodium, it's salt now. And so that's a compound together. So they're written together. So that's the same thing here. This here is called hydrogen chloride. So that's hydrogen and chlorine together to make a single compound. Okay, and that's the same thing like with water. So we don't want to mistake oxygen and water. They're 2 different things. Oxygen is O2, water is H2O, right? We don't breathe water, we breathe oxygen, right? Okay, so here's an example of barium and chlorine. So if we put them together, we call it barium chloride. And so we write it as BaCl. And so that's an example of formulas. Okay, so the atom is going to be the smallest particle of an element. And then we use atoms can be combined to make an element, right? And so we can make a diatomic element, or we can use atoms combined to make a compound, right? So 2 different atoms will make a compound. A molecule is going to be the smallest unit of particles of a pure substance. They can exist independently and possess identity of that substance. And a molecule is going to be composed of 2 or more atoms. It doesn't have to be this, it can be the same atoms or it can be different atoms. So long as it's two or more. So there's a law, it's called the law of constant composition. Let me clear. Sorry. Okay, so when we talk about a compound, such as sodium chloride is always going to be made up of sodium and chloride. And those masses are going to always be proportional. So whether I have a ton of sodium chloride or if I have a teaspoon of sodium chloride, the mass of the sodium to the chloride is always going to have a proportionality to them. Okay? And so that's going to be the law of constant composition. Okay. So when we talk about charges, so often we'll be talking about positive charges and negative charges. So these are going to be our electrostatic forces. So they're going to be forces that are going to either attract things together or they're going to repel things. So if we have an electric charge that are both positive, two positives are going to repel each other. Okay. But a positive and a negative are going to attract each other. Okay. So positive and negative come together to attract. Two positives are going to repel, and two negatives are going to repel. Okay. And so they've done experiments where they've actually had a silk cloth, and then they're going to rub the glass rod with the silk cloth. Now, electrons are going to be transferred from the rod to the cloth. So then it leaves the rod positively charged. And so the pit balls, they're going to have a negative charge associated with it. So they're going to be attracted to that positively charged rod. And so they're going to come together. So then after that, you're going to have each of your pit balls, because the electrons that were there have been moved over to the rod, they've been pulled away. And so now you have two pit balls that will actually repel each other because they're both positively charged. Now, if we take a fur and rub that with a rubber rod, then the electrons are going to be transferred from the fur to the rod, and then that's going to leave our rod negatively charged. And so then when we touch it with our positively charged pit balls, then those pit balls are going to attract to the rod. Okay, so then opposites attract, and then same repel, same charges repel. Okay. Okay. And the next thing we're going to be talking about is energy. And I'm actually going to stop here and we'll finish this up next week. So your exam, you guys are going to have an exam next week. It's going to cover primarily chapters 2 and 3. And it's going to be a little bit of, I think it's 7 and a little bit of 8, which is balancing chemical equations. So I'm going to put a couple more practices of chemical equations. I'm going to put up a practice exam. So your practice exam will probably be going up on Friday, your Friday morning, and the exam won't be due until not this Saturday, but next Saturday. So I want to get a chance to talk with you guys again. So we'll be starting back at energy, and then so we'll be covering energy. So we have about 30 more slides. So that's going to be about an hour lecture. That's going to be left with this, and then we'll have 2 more. There's no class on Monday, so if you guys are planning to come in the lab, there won't be anything there. I won't be there, you won't be there, so I'll be sending an email to remind you guys that later on.
And no lab on Saturday.
And no lab on Saturday. Yes, I won't see you guys this Saturday either. Yeah, for those who are at Harnell. So no labs this weekend. So take the weekend, relax, get caught up, do what you need to do, you know?